Right. Thank you everyone for being here. Today, what I'd like to do is to have sort of a presentation that's very light on proofs and sort of more heavy on characterizations and results. So we'll talk about a lot of we'll discuss. We won't really establish much of what we say. That said, all of this is covered in detail in Gualtieri's thesis, and some of it's also in Cavalcanti's monograph that is in the course materials. Okay, so more specifically, what we'll do is first we'll have a very quick review of the definitions and equivalent conditions, so that's sort of here. This isn't a review just for review's sake. We're going to be using, in some cases, the details of these definitions, so it's good to have them up. Then we'll talk about how generalized complex structures on a smooth manifold can be seen as complex Dirac structures, satisfying a certain condition that pertains specifically to the complex setting. Third, we'll discuss how the Courant bracket can be somewhat naturally obtained through, or can be naturally obtained as an extension of the Lie bracket on vector fields by means of our Clifford multiplication. So this, I think, is very, very, very interesting because it will kind of explain or account for the naturality of the, I think, mysterious Courant bracket. And then fourth, if we have time, we'll discuss how generalized complex structures yield not just algebroids, but bi-algebroids. So special pairs of algebroids on our smooth manifold M. Okay, so let's jump into it. So beginning with a quick review of the definitions and equivalent conditions. So our key definition, the key definition of the course or the seminar series is that a generalized complex structure on a smooth manifold M is nothing but an assignment to each fiber of the tangent bundle of M of a linear generalized complex structure. So recall that that is an orthogonal linear complex structure on the double of each fiber of the tangent bundle. So that double is going to be the tangent fiber plus the, or direct sum, the cotangent fiber, in such a way that the plus I eigenbundle L of our orthogonal linear complex structure in the complexified extended tangent bundle is Courant integrable. And so Courant integrability is here. Well, so that means that it's preserved under the Courant bracket, and the Courant bracket, as a reminder, is listed up here. It's defined on sections of the extended tangent bundle, so those are vector fields plus 1 forms, and the bracket is given by the, so first of all, the Lie bracket, and
recording in progress.
Then the and then these other three terms here, which we discussed last time. Yes.
So I think you forgot to write a vertical bar for the double tangent bundle.
Here?
Yes, right.
This is the tangent bundle.
Oh.
So a linear generalized complex structure on the tangent bundle is a orthogonal.
Yes. On the double.
Yeah. On the double. But that's but that's good notation to introduce. So in some but not all of the references or like source material on generalized complex geometry, there's a pattern of notation where we use say, I don't know, it's like black bold or two lines on the left-hand side in our letters, to designate the double of that vector space. So 2 lines V would be defined to be the double of V, which for us we're taking the definition of that to be the direct sum of V and its dual. So in particular, 2 lines T, so this is a T with 2 lines there, of M is the extended tangent bundle.
Can you repeat what means Courant integrability?
Yeah, I'll write it down. So L, I'll write it this way. Yeah, let's just use the notation. So our subbundle L is Courant integrable, or is said to be Courant integrable when L is when any section of L paired with any other section of L is again a section of L. So it's preserved under the Courant bracket. And by the way, so along with this, so in accordance with this notation, the Courant brackets are sometimes distinguished from the standard Lie bracket on vector fields by also having these 2 vertical lines like that. Let me see. So this is what it means to be Courant integrable. Or maybe involutive is a better term here. Okay, so this is sort of the stuff that we saw before. We see that the construction of a generalized complex structure on a smooth manifold has 2 components. First, there's an assignment of a fiber structure, or of a linear structure to the fiber to the fibers of the extended tangent bundle on M, and then we impose an integrability condition on that assignment. If we drop the integrability condition, then we say that we have a almost generalized complex structure. All right, so this is sort of review. And then we have, let's see, so three characterizations of a linear generalized complex structure. What I want to do right now is sort of move to the third, the one in terms of lines of pure forms, or canonical lines of pure forms. So the first characterization of a linear generalized complex structure is simply the definition right there. I'm going to give the orthogonal linear complex structure a name, J. The second characterization let's see, so let's call this first characterization. So second, we can define, or we can characterize linear generalized complex structures in terms of, or as isotropic splittings of the complexified double of V. that are of this form. So an isotropic subspace L and its conjugate L bar. And the picture. And then we have a isotropic subspace L and its conjugate. And then it can be shown that the pairing, or the canonical pairing, symmetric and non-degenerate, on the complexified double of V identifies the conjugate of L with the dual of L. And then we'll use this fact later, so I wanted to mention it now. And then finally, the third characterization is in terms of a canonical line, an admissible canonical line of pure forms. And I'm not going to write down the details here, but I'm going to put the picture, which is like this. So basically what I want to do is to illustrate how these two are connected, because I think it was a little mysterious before. So again, we have the complexified double of V, within which sits the complexification of V and the complexification of its dual. We have L, an isotropic subspace, which splits the complexified double with its, when summed with its conjugate. And we construct the Clifford algebra. So now I'm thinking of, the complexified double as sitting inside the Clifford, the complexified Clifford algebra of V. So this notation here denotes the complexification of this algebra. This is a very schematic diagram because, of course, 0 here is identical to the 0 down here, but so this is like the 0th level, the first level, the second level. It gets bigger as we go up. And we're acting by Clifford multiplication, C, on the space of spinors, S, which in our case is the exterior algebra of the dual of V, complexified. So complex exterior forms. Here's 0. Oops. We have an and then we find an element rho in our space of spinors. We take the line generated by rho such that our maximal isotropic subspace L is the annihilator of this line. So L is the annihilator by a Clifford multiplication of rho. and indeed of the line generated by rho. So K, K is the complex span of rho. This is the canonical line associated. This is the canonical line of pure forms, or the canonical line of pure spinors associated to L. So,
So you say that L acting on K is 0.
yeah.
And that's the only
Yeah, great.
line that has this property with respect to L.
Those are the only points here that have that property. Yeah. Okay, and then we recall that the action is given by let's see, V plus alpha dot rho is defined to be the interior product of V with rho plus the exterior product of alpha with rho. I think the picture helps a little bit just to sort out where everything is, and also to see how this canonical line framework or formalism, how it relates to the, I think, easier or more immediately clear previous formalism with just isotropic splittings of the complexified double. Okay. So what I'd like to say now is that when we move from the linear setting, so this is everything here is purely linear. When we move to the setting of generalized complex structures on manifolds, so that V is so V star is the cotangent bundle, and we're looking at the complexified exterior algebra bundle. The bundle given by the complex rank 1 bundle given by the assignment of these canonical lines is called the canonical bundle. It's the canonical line bundle associated to the associated to the generalized complex structure. So this extends the notion of the canonical bundle in complex geometry, and so that's, I think, quite interesting. This is already quite interesting. And in that setting, the Courant integrability condition is given in the following sense, or in the following way. So, in fact, the Courant integrability of L, this is easier notation. Is equivalent to the following condition in terms of Clifford multiplication. So for all local sections rho, of the canonical bundle on M. So recall this is a subbundle of the complexified cotangent bundle. There exists.
And it's the line bundle, the top power of the tangent, the cotangent bundle?
Not necessarily.
Okay.
It is in the case of a complex, like when this is a complex structure in M, but for a generalized complex structure, I don't think it's the case that it always coincides with that. Let's see. So yeah. So there exists a section of the complexified extended tangent bundle. Such that, so again, this is local section. The exterior derivative of rho, this should be a nowhere vanishing, let's see, rho. Nowhere vanishing. The exterior derivative of rho is equal to the, can be given by the via Clifford multiplication of E on rho. So I guess in some sense it's saying that the exterior derivative, when applied to sections or non-vanishing, nowhere vanishing sections of the canonical bundle, can be achieved through Clifford multiplication.
So you say K is the canonical line of pure forms,
Yeah.
right?
Yeah.
And then we take a section of.
Yeah. So rho is a trivialization. It's a local trivialization of K.
And this K is canonical line for L, yes?
Yes. Yeah. Or we could say it's the canonical line for the for J, our first definition of generalized complex structure.
So and okay. The K can when we change the point, K can move inside the direction of K as a subbundle.
It's not clear what that means because we're in different fibers, so it's not clear what it means for K to J instructions.
Okay.
What is gamma local?
Oh, just a local section. So gamma being sections of a bundle, and I've just written log for local sections.
Okay.
Okay. So this would be by this I mean sections over some open neighborhood in M. So the section doesn't necessarily have to be defined over all of the units of M. Okay. So this is the first section. Now I want to talk about generalized complex structures as complex Dirac structures. But I think because of, so thinking about space here, I'll actually jump to the third point, because I think that will take one board, which we have. And because I don't want to miss it, it's very interesting.
And so also, K can be multigraded. It's not necessarily. Oh no, it's a
Yeah.
dimension.
Yeah. It's just a one dimension. It's just a subspace
Okay.
of the complexified exterior algebra bundle.
But so my point is, it can only have rho as so rho is a differential form.
Yeah, a complex differential form.
It can only have it is homogeneous differential forms. I mean, there is only one degree.
Not necessarily.
Not necessarily.
No. I think actually that when our generalized complex structure comes from a symplectic structure, then we get stuff in every degree, I think.
I see. Okay.
Yeah, and then the reason why it has to, well, okay, so it has to be nowhere vanishing. I guess I didn't need to write that condition, because if it were vanishing, then the annihilator would be the entire space, and that doesn't fit into our, it wouldn't correspond to a generalized complex structure. Okay, so this, I think, is a really interesting point. The Courant bracket and Clifford multiplication. So we're going to see how the Courant bracket can naturally, how it naturally arises. We won't look at the details, but you can see Gualtieri's thesis for some of them. So 3. The Courant bracket and Clifford multiplication. Okay, plane. The Courant bracket is the natural extension and I mean this in a non-technical way. So the Courant bracket is the natural extension of the Lie bracket to sections of the generalized tangent bubble. Okay, so to do this, recall, or to see this, recall that for all vector fields x and y on M, and all differential forms alpha, we have that there. The interior product of x and y with alpha is, just using the properties of differential forms and these standard operations, is the commutator of the Lie derivative along x and the interior product with respect to y of alpha. So just writing that out, that's Al x iota y alpha minus iota y Al x alpha. And then recall that we can, and then we use the Cartan homotopy formula to rewrite the Lie derivative as written in the following way. So that's d ix iy alpha plus ix d iy alpha minus iy dix alpha minus iy ix d alpha. And now, and in fact, this we can define the Lie bracket on vector fields this way. note that here there's no Lie bracket. This constitutes a characterization of the Lie bracket on vector fields. And the second thing to note is that this is Clifford multiplication. This is the Clifford the interior product of these vector fields with the differential forms is in terms of in terms of the framework that we've set up, is the Clifford multiplication of those vector fields considered as sections of the Clifford algebra of the extended tangent bundle. So we could rewrite this in the following way: xy dot alpha, where this is now Clifford multiplication. This is d x dot y dot alpha plus x dot d y dot alpha minus y dot dx dot alpha minus y dot x dot d alpha. And so, okay, so again, we were told x and y are vector fields. And now we extend this formula from the tangent bundle to the extended tangent bundle. By just replacing the vector fields with sections of the extended tangent bundle. So now these are vector fields plus one forms. So we have a characteristic equation. I'm just replacing x with a and b, and y with b. So now A and B are sections of, okay, so I guess complexified extended tangent bundle. And this actually characterizes, there's only one choice for what this bracket here has to be. So this is the Courant bracket, and indeed it has to be this. So this is one way that we can see, or that we can obtain the Courant bracket naturally as an extension of the Lie bracket on vector fields to sections of the extended tangent bundle. And this, I think, is the only account for the construction of the Courant bracket that I'm seeing. Yeah, you're right.
So I assume that the last formula you wrote is the famous formula of defining the representation, like the bracket of A and B is AB minus BA, acting on the alpha, or
Here I'm taking the approach that we don't have a definition of the Courant bracket, and that we just want to extend the Lie bracket from vector fields to, I guess we might say extended vector fields to vector fields plus 1 forms. And so the approach is to obtain, or to write down a formula which characterizes the Lie bracket for vector fields, and then just to extend that formula to the setting of the extended, to sections of the extended tangent bundle, and then it's I suppose it's a fact.
But so what? How is the Clifford multiplication?
The Clifford multiplication is already defined.
From?
Just from our. I mean, it's already there. We're not defining Clifford multiplication. We're just defining the Courant bracket. So the Clifford multiplication is just as it is here.
Okay. Okay.
So when we have, because yeah, the observation is that when we have a vector field, so that this alpha component is 0, that's the interior product.
Right.
And so we replace all the interior products here with Clifford multiplications, and then we say, well, we're just going to extend that to.
But so why don't you have? Why do you have either Durand differentials and? You think? Why don't you have iota x iota y alpha minus iota y iota x alpha?
Here?
Yes.
You mean? I mean, because I specifically wanted to, in this exposition, to replace, or to describe this formula in terms of Clifford multiplication, because we don't have a interior product of alpha with that's not even example. Let's say beta with alpha. I can take the interior product of a vector field with alpha, but I can't take the interior product of a 1 form with alpha. So I can't extend this formula by writing iota a.
But so where do you see on this formula that we have a Clifford representation?
You mean how did I go from here to here?
No, from the second formula.
This one?
No, the second one. Yes.
Okay.
How do you see? You say that okay, there is a Clifford multiplication.
Yes.
Fine.
Yeah.
But does this formula say anything about is it a statement about the representation of the Clifford algebra of TM, or?
Yes, I suppose. I mean, it's an equality between two expressions of the Clifford multiplication.
I think the point is when we see on vector fields the action of vector fields by Clifford algebra, just EI.
That's right. Yeah.
And because of that, we can go from the first line to the second and replace just y2 dot, because it is the same for vector fields.
Yes, that's right.
And after that, we want to generalize and write the same formula, but not for just vector fields, but for all sections of extended tangible bundle.
That's exactly correct. Yeah, that's precisely right. Like I can't write. So in the first formula, I can't just substitute x for I can't substitute a for x and b for y, because that's a meaningless expression. I can't take the interior product of a covector with another covector. So I can't formally extend this by just substituting a for x and b for y. But when but I can do that when we're talking about the Clifford multiplication, because then in this context, it does make sense to talk about the Clifford multiplication of a dual vector field, say beta with alpha. So the insight, or the interesting step here is just noting that that the interior product is Clifford multiplication, and then once we rewrite this in terms of Clifford multiplication, we can extend it immediately. And then of course there's a whole bunch here that's been swept under the rug. So it gives us a unique, well-defined bracket here, and that unique, well-defined bracket is the Courant bracket. So that's of course something that would have to be established. But we're taking the Clifford multiplication to be already implicit in the structure of the extended tangent bundle. Are there any questions about this? Any more questions? No?
Why this formula gives us brackets?
So we have brackets on a sub-bundle of the exterior of the extended tangent bundle. That sub-bundle is in particular the actual tangent bundle. And we just want to extend those brackets from sections of that sub-bundle to sections of the full extended tangent bundle. So the naive way to do that is just to say, okay, well, let's allow ourselves to plug in any sections, not just of the tangent bundle, but any sections of the full extended tangent bundle, and then see if it works, and see if it gives us something unique and well-defined. And then it turns out that it does.
So we can use this formula as a definition?
Yes, yeah. But it wouldn't be a really great definition, because it's more of a characterization, but it does uniquely characterize the Courant bracket.
Okay.
And so this, I think, is quite nice. And again, I think it's interesting that how essential the all of this Clifford multiplication, like the spin geometry material, is to just the definition, like just to characterize or to obtain the definition of the Courant brackets. Okay, let's take a short break, and then we'll skip part 2 and just sort of discuss part 4. It's pretty short and it's quite interesting. So short break.
Yes, but he said at the beginning, we may use one up there that this lecture would be a proof less. There would be no proof.
Okay. Now I'd like to sort of return to a topic that we talked about before, namely algebraics. And I think I had mentioned that in our context, or in the context of generalized complex geometry, we're going to see more complex Lie algebraics rather than real Lie algebraics. And in fact, we'll see that in this setting, our Lie algebraics come in dual pairs, or sort of special dual pairs, called bi Lie algebraics. So these are going to be pairs of Lie algebraics which satisfy a sort of mutual compatibility condition. Right. So first, let's recall some properties, or the properties that we had outlined last time regarding the Courant bracket on the extended, on the complexified extended tangent bundle. So we have the extended complexified extended tangent bundle on M. We have the data of a Courant algebroid given by that. So that's extended tangent bundle. The Courant bracket, the canonical pairing, and the anchor given by just the projection. So the properties that we saw were first that we have a bracket homomorphism condition, so that fiber-wise image of the Courant bracket. Okay, all right, the double lines for the Courant bracket. The Courant bracket of A and B is the Lie bracket of A and B In this case, this is basically the restriction of, pi is basically the restriction to the tangent bundle component of A. So 2, the Jacobiator of A, B, and C is equal to the exterior derivative of the Nijhuis tensor, which I'll just write it out like this. 1/3 d A, B, C plus cyclic permutations of these terms. Third, we have an almost Leibniz condition, that is A FB is given by F AB plus pi A F times B, so this is multiplication, minus, and then, so this would be an actual Leibniz condition, but then we have this extra term here, so minus the canonical pairing of A with B times F. Fourth, that the canonical pairing of DF with the DG for F and G, two smooth functions on M, vanishes. And then lastly, that the projection of A to the tangent, to a section of the tangent bundle, so a vector field, applied to the natural pairing of B and C is given by this expression. Okay, so what I'd like to do is to explain and to show, so this is a little bit more of a demonstration, how a generalized complex structure on M corresponds to a sub-Lie algebroid of this Courant algebroid. So we won't care about these conditions. Don't care. For now, don't. But we do care about three, because these first three conditions are sort of like their adjustments. Well, the second and third are actual the algebroid condition. Namely, for the algebroid, we need the Jacobiator to vanish. We need the Jacobiator to be 0, because that means that we have that our bracket is a Lie bracket on sections, which is what we need. And we need to have a Leibniz condition, so that means that we need this term to vanish. The first term is perfect as it is. This is the condition. This is the Lie in the context of Lie algebroids. This is the Lie algebra homomorphism condition. So this is actually quite quick. Note that if since Since our the plus I eigenbundle of our generalized complex structure is, so first, isotropic, and second, Courant integrable. We obtain that, so I'm going to call this star, and I'm going to call this double star. Well, integrability implies that the bracket of A and B.
I think that double star is there is missing because you have a function there. This is a function, double star, a smooth function.
Yes.
While on the left hand side of the you only have vector fields and transfer points.
Let's see. Oh.
Oh yeah.
Yeah, there we go. Okay. So, and this should have been a star, not a double star. So integrability implies that the bracket of A and B is again a section of L. So again, like an L. So this is from integrability. So 1 implies this, and then 2 implies, so 2 being that, this 2 implies that. Then 1, then because L is isotropic, and we have 2 sections of L, that means that this is equal to 0. So that then implies that the Jacobiator that the Jacobiator vanishes. The Jacobiator vanishes when we plug in sections of L, and equals 0. For all sections of L. And then for double star, it's the same thing, but easier. AB equals 0 by the isotropic condition. And this means that our formula becomes A F B is equal to FAB plus pi A applied to F times B. And this is the Leibniz condition. So because then that last term vanishes. So then both of these two facts together yield that L and the Courant bracket restricted to L, or to sections of L, and then the Courant anchor map restricted to L is a Lie algebroid, a complex Lie algebroid. So that's interesting. And we don't have enough time, but it can be shown, like, so it's straightforward to show that L bar, that the same is true of L bar. As we noted earlier in the lecture, the non-degenerate pairing, which has nothing to do with the Lie algebroid structure, but the non-degenerate pairing on the Courant algebroid given by the complexified, generalized tangent bundle, identifies L bar with the dual of L. And the pair L and L bar is what's called a Lie. These are complex Lie it is a complex Lie bialgebroid. So I'll just sort of say descriptively that a Lie bialgebroid on a smooth manifold is a pair of Lie algebroids L and its dual with the property that with a certain well, we do have we have time to write this down. So definition.
So like L bar, L star is the complex dual. Oh, the
real.
The linear forms.
Yeah.
I see. Okay.
Yeah. Okay, so definition. A Lie bialgebroid, and so this is real. We can make it complex in our minds. Bialgebroid on M is or consists of a pair, a dual pair of the algebroids L and L star on M, such that, or subject to the condition that DL applied to alpha beta, this is the bracket on the dual of L, that DL is a derivation with respect to this bracket. And I need to define what I mean by DL and what I mean by some terms on this other side. So where the bracket, particularly over here, bracket is the Shenton bracket. Am I saying that correctly? Shenton? Scouten? I think.
Oh, that's what I heard by a professional mathematician.
I've never heard it spoken before.
I trust them.
Shenton Bracket on the exterior algebra bundle associated to L star. So this is given by, it's basic, it is the naive generalization of the Lie bracket to the exterior algebra. Given by, let's see, alpha 1, oops, alpha 1 wedged through JK, A K, alpha K, beta 1 wedged to beta K, defined to be the sum over I and J of every combination of taking Lie brackets that there is. So that's accounting for the antisymmetry, -1 to the power of I plus J, alpha I beta J, omit alpha I, which okay, so the Shenton bracket is we have exterior. We want to apply the Lie bracket to these to wedges of elements. On the elements themselves, on the space of elements themselves, we already have a Lie bracket. So what we do is, well, we take the Lie bracket between every pair of elements here. So we pull those two elements, an alpha element and a beta element, out in front. In order to do that, we pick up a term of -1, depending on how many times we cross over the other elements. And then we just sum all of those terms up. So that's the Shenton bracket. And then the Lie algebraic derivative is defined in the same way as the standard exterior derivative is. So dl is the so that for a section sigma of the kth exterior algebra bundle of L star, and for sections xi of L, dl sigma is characterized by the following quality, namely that when paired with x0 through xk, it's given by the familiar formula for the exterior derivative. Okay. Oh. Okay, so it looks kind of messy, but the idea I think the idea here is that we're just taking each of the elements, each of the arguments, and we're applying them as derivations to every term in sight, to sigma, and to all of the other arguments. So applying it, and everything combined. So in order to apply it to sigma, well, first we need to push it down, or in order to apply it to this expression, we need to push it down to the tangent bundle. So then it's a derivation on functions that accounts for the first term, and then we apply that term xi to all of the other arguments as derivations. In any case, so this then gives us the this is then the required property, required compatibility property between the two Lie algebroids, which together constitute a Lie bialgebroid. And then as mentioned at the beginning of this section, L and its complex conjugate then form a Lie bialgebroid pair, a complex Lie bialgebroid pair. So this is, yeah, it seems like there's a lot of rich stuff happening. Are there any questions about this? I think we're a bit over time.
So the natural question is, when we have such a Lie bialgebroid inside a Courant algebroid, does it define the generalized complex structure?
Well, I mean, this is...
So the reverse, we have shown that given a generalized complex structure, we have L, right?
Yeah.
Which gives a Lie bialgebroid.
Uh-huh.
Is it a one-to-one correspondence?
Well, in order to have this identification between the conjugate and the dual of L, I think we need L and the conjugate to be isotropic. So, because and they need to split. So I think my sense is that the answer is yes.
Okay, good.
I think the answer is yes. But there's actually a lot to say apparently about Lie bialgebroids and Courant algebroids. Apparently, we can also that given a Lie bialgebroid, we can take their direct sum as we have here, kind of, and obtain a Courant algebroid from that direct sum. So there's a close connection between Courant algebroids and these Lie bialgebroids. They're like the Lie bialgebroids seem to be a sort of like a very nice decomposition of a Courant algebroid. All right. So I think I'll note at this point that I think we've sort of done our. This has been kind of our introduction to this material. At this point, I think we can go in a lot of different directions. One direction could be to revisit a lot of the material that we've looked at and do it very rigorously, sort of like a course, because this really isn't a course. Another thing that we could do is look at some topics and maybe explore those other topics. So we can also discuss this in the Telegram chat. It's something to think about. All right.
There are some beautiful results in this theory, you know.
I'm not familiar enough with it to know. I think that pretty much everything that we've seen here today is very, very aesthetically nice. But I don't know if there's some like big result or like some result that connects this material to some other field like in a surprising way. But we can think about this and we can look at it and
so I think I think you know that in symplectic geometry, Lagrangian submanifolds are a particular tool, right?
Yeah.
So I think this is exactly kind of much has to do here with
Generalizing Lagrangians. Yeah, that's right.
Or direct submanifolds or.
This is a good point. Actually, that might be the best thing to do next, to look at special, to look at special submanifolds of generalized complex manifolds. I think that's actually one of the motivating. Yeah, I think that in a lot of the material that uses this, just from what I'm just like from looking through some stuff, this notion of these different kinds of special submanifolds is really important. So actually, that's what we should do next. We should talk about special submanifolds.
Because so far we have defined what is a generalized complex structure on a manifold through different perspectives.
Yes.
Okay. So yeah, I think looking at the submanifolds would be.
And it's non-trivial also. The submanifold material. Yeah.
Right. Because I think this is important. I don't know about it, so I'm also.
Yeah. Me too. All right. Great.
Well, why we call this
Generalized
complex geometry? Is some geometry particular case of this? Why is generalized?
Oh, because it's a integrable complex structure on the extended tangent bundle, where a complex manifold is an integrable complex structure, or an integrable assignment of almost complex structures to the tangent bundle itself. It's generalizing the notion. It's generalizing the construction of a complex structure by instead of just looking at the tangent bundle, we're allowing us to use the extended tangent bundle. It's complex geometry on the extended tangent bundle. It could also be called generalized symplectic geometry because it generalizes both. I think I've seen that any situation where people are working on the generalized tangent bundle, the extended tangent bundle, they call it generalized geometry. All right, so see everyone next week.
Can I ask a question about the definition of the algebra?
Yeah.
Is that definition symmetric with respect to L and?
Yes, it is. Yeah. Yeah.
Because the brackets, the dual of the differential is the brackets. So the bracket on L star is, in the formula you can change L and L star and it's the same,
Fine.
Yeah.
the same formula.